So
All right.
okay. Go ahead, Ulf.
Yeah. Hello, everybody. Welcome to the lightning talk of the Kernel Working Group in Dinaro. So I'm Ulf Hansson, working in the kernel team, being contributed to the kernel for quite a while and subsystem maintainer for a couple of different subsystems. So before I go into the topics for today, let me just give you a very, very brief overview of KWG. So we're not the only team in Dinaro working on the kernel, but usually we take on more long-term development tasks in KWG and work on infrastructure code rather than drivers and platform-specific code. And we also do a lot of subsystem maintenance. Yeah, that's it. I think we can go into the topics.
Yeah.
Can you move to the next slide?
Is it okay now?
Yeah. Okay. So the screen is flickering. I'm seeing your face all over the time. Vincent.
Sorry, you're seeing me?
I'm just seeing you. I don't see the slides.
You should probably mute yourself, Vincent.
Okay, let me go back to the slide because I think I was sharing already them before.
Maybe you need to mute yourself so you don't get seen. Okay. All right. So let's start with a. Oh, this doesn't work. Okay, let me take the slides on another screen. So the first topic is MMC, and I'm the subsystem maintainer for that subsystem. So I wanted to share a little bit of the updates and the highlights that happened since the last 6 months. So in Linaro, we had this Linaro storage evolution project that we closed down in Q1, Q2, and so we're not actually driving any storage work currently. But this is some of the updates that has happened since the last connect. So in MMC subsystem, we got eMMC inline encryption supported, and that's been a collaboration between Google and MediaTek and Qualcomm. From a Linaro point of view, and me personally, I've been working on SD card features, and those has been upstreamed and supported now. And a couple of those features are cache control and power off notifications. And that's about write performance and about graceful power down of SD cards. And then the usual maintenance thing with new hardware being supported and other maintenance things, of course. We also worked on SDUHS2 card support. We are not actually driving this work anymore, but more helping out with giving guidance and things like that from a maintenance point of view. So nowadays it's the community that drives this work, but we are there to help out. So that's it for MMC. So by the way, if you have any questions, just type them in the chat, and I think we're all online here, so we can also answer a question, or if you want to reach out to us afterwards in an email, that works fine as well. So the other topic from the storage project that I just told that we've been closing down is the BFQ IO scheduler. So these highlights is actually being, I'm giving you these highlights on behalf of Paolo Valente, who is the inventor and the maintainer of BFQ in the Linux kernel. So the very good news that I can share is that the community around BFQ has been growing lately. So usually it's been Linaro that's mostly been involved, but we see more and more companies getting involved in BFQ nowadays, and that is really good news for the ARM community as well. Mostly we due to these collaborations, and has enabled a lot of new test environments and other distro deployment that has happened. And because of these things, Paolo has been able to, together with these other companies, improving BFQ a lot. I'm not going into the details of all the improvements, but without being, a lot of significant improvements has been made the last 6 months. Work that has been done before in Q1, Q2, but hasn't really got upstream until quite recently. Today we're working on one extension of BFQ in a joint collaboration with Seagate, who has joined us in Linaro quite recently. That is a new hardware technology for these old HDD devices that's called multi-actual drives, and we're trying to make BFQ work better with these kind of devices. That's kind of the only activity that we are involved with right now. Otherwise, it's just maintenance. And going forward, that maintenance is going to be the important thing that we care about here. And that is something that's going to be important for ARM vendors as well, because of these ARM embedded devices that has these kind of storage devices attached to them that could benefit a lot from using BFQ. Yeah, I think that's it for BFQ. We can move to the next slide, please. So now we're moving into the power management things that I've been involved with. And CPU cluster idling is one of those topics that we've been working with quite a while in Linaro. Since quite some time back, we have moved into more of a platform deployment phase. So most of this infrastructure code has been upstream for quite a while now. And now we're seeing more and more platforms deploying this support. And during the last 6 months or so, we have been collaborating a lot with STMicro and a couple of members engineers from them, and trying to help them to get their support upstream for this thing. That said, during this deployment, we discovered a lot of new corner cases and problems and bugs in the common code. So we're trying to fix those as a parallel activity with helping them. Other activities in this field is that we have this public trusted firmware software that didn't have this PCI OS initiated mode support, and that is something that STMicro is helping us to drive as well. So a couple of member engineers from STMicro is involved in this activity. But we're actually looking for more collaborators in this field. So if this is something that is interesting for anybody else, just please reach out to us. So I think that's probably what we've been doing in this field in a briefly way to describe it. The next thing that we will intend to look into is more performance and energy optimizations that we have a list of things that we believe could be of value for platforms that is using these features that definitely could improve the behavior a bit. So that is something that we will look into as the next step. All right, Vincent, please, next. All right, some words about performance states in GenPD as well. This DVFS and OPP thing that's been upstream for quite a while now. This is a work that we've been doing in Linaro quite a while ago. So the core infrastructure support for this thing has already been upstream for quite a while ago. While we did that, we only had some basic platform deployment that got upstream, using these new interfaces and the way of dealing with DVFS. Luckily, we have lately seen some movement both from Qualcomm and NVIDIA taking full advantages of these new interfaces that we have been adding. And me personally and Brijesh Kumar has been trying to help out, giving guidance and reviews when this platform deployment series reaches the mailing lists. And during these kind of discussions, we realized that there is, again, corner cases and other small bits that is missing in the full in the common infrastructure code that we trying to help and get those pieces that is missing upstream as well. So I think that is very valuable because of we actually get a full reference implementation with these platforms, so other vendors can have a look at as well. So hopefully we'll see at least the NVIDIA platform getting this support in the 5.16 kernel. So it's very close to get upstream with this. So I just wanted to share that news because I think it should be interesting to many other ARM vendors as well. During this task, as I said, we have also realized that there is quite some room for performance and an energy optimization for when you look into some of these corner cases that we discovered. So this is not something that we have planned to work on, but we might do as a part of some maintenance activities for these subsystems. So that's it for this slide as well, I think. So now we'll talk a little bit about something new activities that we're looking into. So something that we call power sequences for discoverable devices. So this is more like a sales pitch for new work that we could take on in the KWG team. So just to give you a little bit brief background on what this is about. So we have these kind of discoverable devices like a Wi-Fi or Bluetooth devices that could be attached to an interface like PCI or USB, UART, or SDI. And the typical thing with these devices that need some kind of specific device-specific power sequence to be carried out before they can be probed and detected. So these devices cannot be supported in the kernel as is today. So it means that there is a lot of devices that simply doesn't work. So this little task that we're looking into is more or less trying to find a common way to support these devices. And as I say here in one of those bullets, that for SDIO we have a subsystem specific way to deal with these devices. There is also subsystem specific DT properties for this. And that is my invention several years ago, and that's probably not a good invention, but that was happened. So what we're trying to do now is to do more common and the right thing, so it can be used for other subsystems too, like PCI and USB and UART. So we have seen movements in this field from Qualcomm, and they are eager to get some of their Wi-Fi and Bluetooth devices supported upstream. And I'm pretty sure that there's a lot of other devices that could benefit from this too. So if this is something that could be interesting to you for us to work on, please reach out to us, and we'll definitely try to get your device supported as well. So this is just in the beginning of the development, and we'll see where this leads. We have another guy from Qualcomm that is driving this work. So currently we were just me as a KWG member is just reviewing and giving guidance on where this should go. Yeah, that's it for me. And then I think it's Daniel that can talk to you a little bit about the thermal activities.
Yeah, thank you all. Yeah, so last year we introduced a new mechanism for notification from the thermal to user space, because that was something which was missing, and because of how the thermal needs to be managed also in user space, the different SOC vendors were hacking the kernel. So we provided a new mechanism based on Netlink. Why Netlink? Because Netlink is we have all the stack with the sockets, so we can use the main loops and do event-based code. So there are 3 channels for these netlinks. So that means we don't have to. Well, we can do some discrimination with the events and don't take care of all of them. So we have the events. So this is typically what is interesting user space, so this mitigation and the trip points when the trip point is crossed in one way or another way. The thermal zone when they are created or destroyed, that happens when we load or unload the module. Or we have events like thermal zone disable or enable, that happens when we are resuming and suspending a device. On the other side, we have the commands allowing to do some configuration and get the configuration of the system directly. That's something we can also do from sysfs, but thanks to that we can have, well, we can, for example, for security reasons, just use netlinks instead of exporting sysfs. Also, we can get the temperature of the thermal zone. And for compatibility, we have a sampling channel to get the temperature of the thermal zone when they are actively monitored from the kernel. So, but that's now obsolete, as we have all sensors are working with interrupt mode. So we have an event from interrupt directly, so we don't have to monitor the thermal zone temperature. In addition to that, because the Netlink are a bit complex to deal with, there is an abstraction layer to abstract this protocol, which is providing simple functions based on just on events. So we have just to provide callbacks, and this library is also, we can mix the main loops. So we provide a way to create a main loop from the library itself, or we can use the file descriptor API to get the different file descriptor from the library to put that in our main loop. So the question is where we should host this library to maintain it. So the first idea was to put that in the kernel source tree, but there is dependency with the library, the Netlink library. So not sure it's the right place, but yeah, so it's still under discussion. Otherwise, we can put that with the other tools we find in kernel.org. The importance of having this hosted somewhere is because Netlink is an ABI. So if we can provide both together, it's better to make sure that, well, there will be matching. Can you put the next slide, please? So the thermal HIL is a hardware abstraction layer. It's Android thing. So it's not. It's a side topic of the kernel, but we have to talk about it because it's the user of the thermal library, and the reason why we make the improvement. I will just go to the slide on my side because it's moving. Okay. So there is a relationship between the thermal zone, the sensor, and the governor, 1-to-1. So that means when we have a sensor, we put one thermal zone and we have one governor. And for this reason, for this design, because the user space needs some events from the kernel, it needs to use the user space governor. And if it uses the user space governor, there is no mitigation done from kernel space. So there is a hack. More people are doing hack around in the thermal framework to create multiple thermal zones for the same sensor in order to put one governor with a different configuration and to get the events. So for this reason, that was not acceptable, because it's at the opposite of the current design of the kernel. And that's the reason why we created this notification mechanism. So all this code, all this hack we have in the kernel is can be removed, and we can use this library to use that. So the thermal HIL is not based on anything existing. So we created now a generic thermal HIL based on a configuration file, which tell us what sensor, what what type of sensor we have. So we have a battery or skin and so on. So we can from there do some generic code and consolidate the thermal agile. So the next improvement is we want to improve also the power agile in order to get and set power on different devices. So I use a daemon which does thermal mitigation, can get information and events from the thermal agile, and then it can take a decision and act on the power on the different device through the power agile. So it's much cleaner in terms of design. And also because the thermal framework has more events, the thermal agile, the existing version of the thermal agile does not support this. So maybe it could be interesting to investigate if we need a new version of the thermal agile to get these events. The thermal agile are versionized API, so we have to make them evolve and keep back and be back compatible with the previous versions. So that's kind of discussion we should have. Done for me.
Thank you, Daniel. So the next topic is the scheduler. During the last 6 months, so we have started an activity around the latency of the audio rendering in Android, and especially how to handle some change in the load in the audio load, like moving from a light number of voice to a huge number of voice, and how to make that handle correctly from a frequency scaling point of view. So we have worked on this with some Google guy working on audio, and also with some student of the University of Modena. There is a pull request right now in SITMARC that expose the plan of the proof of concept that we have worked with, and the results show some significant improvement when we have this switch between the light and the EV load. So we are, as mentioned in the slide, so we have been able to reduce the maximum latency from 100 to 4 milliseconds. So this is the worst case latency, of course. So that one thing that we have worked and we will continue to work on, and maybe the next step for that will be to extend the study also to see what we can do on the display path, if there is a need first, and how we can make that a bit better. So that will be for the ongoing cycle, I would say. Then several changes have been merged in the scheduler since March. And one interesting one is that we have changed the way we are updating the way we are running the background activity for updating the load tracking of the task and the run queue. And we have moved that out of the scheduling step. So when, in fact, during this section, the preemption and the IRQ was disabled, and this update might run quite long, depending of the number of C group and number of updates that have to be done. So we have moved that out. So now we have a shortened schedule duration when we are moving to idle, and this enable interrupt to be handled earlier. So that's it. Then there were also a lot of improvement in the fairness between a group which were moving in and out throttling state, and especially there was some corner case where instead of having a 50% share of runtime between two C group, in some case, one of the group was getting less than 1%. So normally everything now has been fixed, and this can be used without any problem. So we have also worked, it's not mentioned in this slide, but we have also worked on enabling the frequency invariant support in the CPPC CPU frag driver. That's a feature that was already enabled on mobile system and also on x86. And now this is available for all in any system that use the CPPC CPU frag driver. So this helped the scheduler to have a better knowledge of the real load and utilization of task, whatever the running frequency. And then we still have a lot of discussion around the wake-up path of a task and how to select an idle CPU, and what is the best way, how much time we should waste on looking for an idle CPU or an idle core, or should we return earlier? So there is a lot of trial and patch set which are going around, and we are planning to speak about that a bit more deeply during the next Linux Plumber conference, during the microconf, the scheduler microconf. And now I'm going to let Matthew continue.
Yes, thank you, Vincent. So moving on with Coresight. So this is a subsystem where there's always a fair amount of churn happening, and the past cycle was definitely not an exception to that. Starting with the perf tools, a lot of things have happened in that area, covering corner cases that had been left behind, not because we didn't want to address them, but because we didn't have the use cases for them. So as more people start using the subsystem, using them in different ways that we hadn't provisioned for, we have different cases or corner cases that are coming up where traces are either not decoded properly, or they're simply things that have to be improved. So Leo Yan and James Clark have definitely led the charge. Bug fixes, as I mentioned, optimization, things are running a lot smoother now with all of those enhancements. So if there were things that were not really working the way you wanted, or maybe you were not seeing the things that you thought you'd be seeing before, have another look. There are high chances, high probabilities that some of those things might have been fixed. Mike Leach was able to complete his feature on system configuration. So this one is very interesting because it allows users to really use the full potential of the Coresight IP blocks. Those come with dozens of configurations, configurables, and it was simply impossible for us to fit that in either sysfs or the perf interface. So this driver is really allowing users to tune their trace sessions to be optimal and really, as I mentioned, exploit all of the capabilities of the chips. It was made to be modular. It looks like a driver, so configuration can be switched on and off at will. That way you're not bloating your kernel, and yet you're having the capabilities that you're looking for, and you're also not impacting other configurations that might exist in the system. So this is just the beginning. There's a couple more patch sets to enhance the base offering that is currently there. But this is definitely sufficient to start exploring the area. There's good documentation. So if you are interested, I'd say this is definitely a good place to start. And Mike, I, and people on the mailing list are also there to help people move along and help be acquainted with the feature. Suzuki Pelusi and Anshuman Kandwal have worked on the ETET-RBE. So this is a next generation IP block. It's a combination of source and sink that are usually going hand to hand with a CPU. So definitely getting closer to the Intel PT architecture in that way. That work right now is all ready to be rolled out, although it's running on the simulator. As of today, we are not aware of any SoCs that are instantiating that. But as I mentioned, it's all there, all ready to go, so that when we do see people coming out with this, there won't be any need to wait. James Clark is currently working on adding support for the perf tools. There are patches floating on the mailing list, and that should be happening in the coming months that we close in on this feature. If we move on to the RP message subsystem, two main features to talk about. First is attach detach. So those are scenarios where we want to decouple the life cycle of the remote processor and the application processor. So that way the application processor can basically go away, be switched off, rebooted. The remote processor driver can be unloaded, and yet it does not affect the service that are rendered by the remote processor. So the remote processor is kept alive, it's kept on, it's doing its job. And when the application processor is coming back online, it can be resynchronized with the remote processor, and things simply go on as they would have been had the remote processor been booted from a cold start. So very interesting for industrial applications, automotive, where we want to have sustainability systems that are fail-safe. That way we don't have to couple the life cycles of the application processor and the remote processor. Arnaud Pouliquet has worked on refactoring the RP message character driver, also known as RP message char. The idea was to split the control plane and the data plane. That was done. It's all ready to go. There are patches on the mailing list. That should be coming in soon in the next kernel version. So the whole idea behind this was to be able to instantiate data planes and service devices from the namespace or the name service interface that is coming from the remote processor. So that way we're adding flexibility, and those services offered by the remote processor can change based on the firmware image that is being run rather than user space. Always a lot of bug fixes, support for new architectures as well, but always refer to the mailing list or the kernel tree for all of the updated or the latest supports. So moving on to our work on VirtIO and the virtualization space. So this is folded under Project Stratos, where we strive to make VirtIO interfaces as standard as possible, so that if you want to change your VMM or your hypervisor, you do not have to rewrite all the glue that interacts with it. We started with three different devices, so I2C, GPIO, and a random number generator. I2C, the specification has been merged. This is work that comes from Intel. Intel and Linero have jointly worked on a driver that was queued for, that was merged in the last merge window. That should come online on Monday when 5.15 RC1 has been released. Interesting there is that there is a Rust backend daemon that runs on guest. So that is implementing the vhost user protocol. That way the VMM can change, the hypervisor can change, and we don't have to change the driver itself. So Varesh Kumar has been working on that. He's also working on adding support for zero-length transfer. So expect that to be happening in the coming weeks. GPIO also, Varesh. Specification was worked on. This was merged. There's a driver appearing once again in 5.15 RC1. Here too, we have a Rust implementation of the backend, also following the vhost user protocol. And from what I understand, there is work in progress to support interrupts. Random number generation, that was done. There was already a driver in the kernel. The Rust implementation has been published. and there is currently reviews happening in the vhost device crate in order to merge that. So the last steps are being finalized. So this is what I have on my side. I am giving the microphone back to Vincent, who will talk about SCMI.
Yeah, thank you. So we are working on running a SCMI server in I would say somewhere else than a dedicated system control SCP or power coprocessor. So for the last couple of months, we have started to work on implementation in various execution environments. So we already work on running this server in a Opti execution environment. So, and we have created a new arch in the SCP firmware for that. So what is ongoing is the way that we'll handle interruption. So there is an interrupt and asynchronous notification support, which is under review in Opti. And we'll probably leverage on this for the interrupt notification. But yeah, that's something that we have worked on already for a while, and that was our first use case. Then another use case that we had was to run this SCMI server as a VIOS user backend. So typically, as just like Matthew mentioned, running that in the host user space and using socket to communicate. So we have also enabled this, so you can create an SCMI backend, VIOS SCMI backend based on this. So we have updated the different architecture linked to that. And the last execution environment that we have, it's a Zephyr VM backend. So we have added the support of Zephyr in the SCP firmware, so you can run this SCMI server with Zephyr in a dedicated in a gas VM, and this support the Virteo SCMI on top of Virteo MMIO, and and we are this can be then bridged with your Linux guest in order to serve some SCMI requests in order to disable some resource, so like a clock or a power domain, or asking for a higher frequency. So that's the three main execution environment that we have enabled. So we sent a pull request earlier this week on this in order to see how we can get that merge in the SCP firmware. And we are focused on the SCP firmware because the goal was really to leverage on the fact that they have already a state machine which followed the SCP specification, and we didn't want to create a new version of that with new bugs and so on. So in parallel, we have also started to see how to integrate the support of device tree in the firmware, and we are investigated how we can reuse something similar to what is done in Zephyr, which which pass the DT during the compilation and create some static configuration based on this. So we have a Mike Leach who is working on this in order to fill the table used by the server. And also, so the last point about Rust is that, as Matthew mentioned, the other backend, Virteo backend and VIOS user backend have been developed in Rust. Whereas this one is done in a plain C code. So even if it has been tested against the MISRE C coding rules. So we were wondering if that would make sense to move this SCP firmware in Rust. So that's really an open question for now. We don't know at all if we move on this or not, and it's more to raise the discussion on this and see if that really was the effort of re-implementing everything in Rust. So we will continue during the next cycle working on this, improving the connection between the Zephyr backend, the Zephyr backend in a VM with a Linux guest, and supporting multi-user from this backend in order to minimize the interaction. So that's it for me, and I will let Arne continue with the next slide.
I'm the maintainer for the ARM SOC tree, co-maintaining this with Olaf Johansson. We take turns pretty much, and this is just an overview of the stuff that has happened over the past year. The most exciting platform that we've merged was for Apple's ARM-based laptops and workstations. We've had a couple of other SoCs. We had still 3 new 32-bit SoC families merged and lots of 32 and 64-bit SoCs in existing families. Also taken the time in the last winter to remove a couple of older platforms that had just not been used in a couple of years. And then we still have a lot of work going into the existing code. So there's some ARMv5 platforms that are seeing very active cleanups and that are still being actively used. Most of the 32-bit work is moving towards the low end. So usually it's the platforms that see the most work nowadays are the single and dual core Cortex A7, but also even older ones. Whereas the larger SMP configurations, they tend to be using 64-bit these days. On the 64-bit side, since there is less cleanup to do and fewer outdated platforms because it's not that old, most of the work is done in adding support for additional features and new SoCs. So it's mainly just adding device tree files to the kernel. We have a couple of platforms. I listed the most active ones here that get hundreds of patches all the time, where people just add new features to each of the SoCs. The SOC tree also merges some drivers. There's obviously the SoC-specific drivers that don't fit in some other subsystem, for example, for identifying which particular SoC you're running on, and firmware that is SoC-specific, but also the reset and memory controller drivers that live in, that are maintained by other maintainers, but that can send us updates for these subsystems to have them merged through our tree. In total, I've listed the number as over 5,000 commits that were merged over the past year through our tree. We had around 600 pull requests that we merged, and we had also around 600 authors that contributed at least one patch. Moving on to the next slide. This is one particular bit of work that Linus Vallée is heading. I'm also working on that a little bit. This is to make the higher end 32-bit configurations work well into the future, where you have more than a gigabyte of RAM. We currently rely on HiMem to access more physical memory than fits into the virtual address space of the kernel's linear map. This will eventually go away as people are focusing on 64-bit, and we try to simplify the kernel, and we try to come up with a way to keep those systems that are deployed already and in use working, using up to 4 gigabytes of RAM. We've talked about this at previous connects, and this is a long-running work. But nevertheless, we have made some progress there. Linus has done a series to move the kernel image into the so-called vmalloc area. This is a different way the memory is mapped. This is one of the prerequisites for it. And this was the first thing that got merged, and I have just finished mainlining the removal of the getfs, setfs helpers, which is another building block that we are going to build on top. Although this work was also started independently on other architectures for other reasons. There are a couple of things that we need to do before this actually becomes usable. Most importantly, we have to rewrite the way that kernel accesses process-specific memory in user space, because as we map up to 4 gigabytes of physical memory into the kernel address space, we don't see any user addresses anymore. And then we have to switch around between the two address spaces every time that we change the context from user space or that we access user space memory from the kernel. And then another thing that will have to happen after that probably is a new way to remap discontiguous physical memory into the available 4 gigabytes of address space if the lowest and the highest address are more than 4 gigabytes apart. And that's it from me. And I think now we have a little more time for questions to any of these topics that we presented.
Yeah, so there was some question on the Q&A which have been answered already, but don't hesitate if you have a few more questions. We have 4 minutes left before the end of the call. So it seems that it's okay. If there is no other question, can probably close.